What if we could perform complex 8-bit floating point multiplication for AI models using nothing but simple integer addition? Today, we break down a paper that achieves mathematically exact rounding without the standard hardware bloat. The researchers demonstrate how operating in the logarithmic domain allows formats like E5M2 and E4M3 to be multiplied efficiently. In this series, we will explore their clever error correction logic and see how this radically shrinks silicon area. To understand this hardware optimization, we first need to look closely at the specific 8-bit formats being multiplied. The figure shows the bit allocation for the two primary formats defined by the OFP8 standard. Both are exactly 8 bits wide, starting with a single sign bit on the far left, labeled S subscript X. In panel A, we have the E5M2 format. Here, the exponent takes up 5 bits, leaving just 2 bits for the mantissa, or M subscript X. Over in panel B, the E4M3 format shifts this balance, allocating 4 bits to the exponent and 3 bits to the mantissa. This structural trade-off defines how these numbers behave in neural networks. E5M2, with its larger exponent, offers a significantly higher dynamic range. E4M3 sacrifices some of that range for an extra bit of mantissa, providing higher precision. Note that while this diagram clearly lays out the bit allocations we will be manipulating, it leaves out details like exponent bias values and special cases. While operating in the logarithmic domain saves space, it introduces an inherent mathematical error. This heat map plots that baseline approximation error for the E5M2 format before any rounding corrections are applied. The horizontal axis, M subscript X, and the vertical axis, M subscript Y, represent the fractional mantissa values of the two operands. Note that these axes map mathematical fractional values from 0 to 1, rather than plotting their literal binary representations. The color of each square indicates the error magnitude, measured in units in the last place, or ULP, as shown on the right. Notice that the error is strictly constrained between 0.0 in the white squares and negative 0.5 ULP in the darkest squares. Because this baseline error is always bounded and never exceeds half a ULP relative to the exact result, the system can exploit it. For modes like round to 0, the approximate result naturally falls into the correct mathematical bin. Consequently, these rounding modes can be obtained directly with zero hardware correction overhead, eliminating the need for extra carry-in logic. While direct integer addition works perfectly for simpler rounding modes, standard round to nearest even, or RNE, requires a slight intervention. This new heat map plots the E5M2 multiplication error when comparing our logarithmic approximation directly against exact RNE rounding. The error landscape here is distinctly different from the baseline. The scale on the right reveals a purely discrete set of outcomes. The error is strictly either 0 in the white squares or exactly negative 1 ULP in the darker gray squares. These negative 1 ULP errors occur specifically at certain tie-break grid intersections, such as when mx is 0.25 and my is 0.50. Because the approximation only ever fails by exactly 1 ULP at these predictable tie configurations, the fix is straightforward. To achieve exact RNE rounding, the hardware just needs to detect these specific mantissa combinations and inject a single bit of correction, a conditional carry-in, into the integer adder. Keep in mind that this specific tie-break handling only applies to RNE. Other modes require different logic. Still, this single-bit intervention keeps the overall silicon footprint remarkably small compared to standard multipliers. We've easily solved the 2-bit mantissa of E5M2, but the extra precision in the E4M3 format pushes this integer approximation technique to its limit. This heat map plots the baseline error for E4M3 multiplication. Unlike the previous 4x4 grids, the M subscript X and M subscript Y axes now form an 8x8 grid to reflect the 3-bit mantissas. On the scale to the right, the darkest squares represent an error dropping down to negative 1.5 ULP. This wider spread fundamentally changes the math. Because the baseline error exceeds a full negative 1 ULP, none of the rounding modes fall naturally into the correct bins like they did for E5M2. Furthermore, this deep error bound makes strictly directed rounding modes, such as round up or round down, mathematically impossible to achieve purely by adjusting the carry-in bit. While the extended color bar highlights the limitations of this logarithmic method for directed rounding, Other critical modes can still be salvaged with the appropriate carry-in logic. To compensate for the varying ULP errors across both formats, the researchers translated the heat maps into pure digital logic. This table maps out the exact hardware blueprint needed to execute the multiplication. The rows divide the two formats, E5M2 and E4M3. The first column defines the base integer addition, which combines the operands, a format-specific constant, and a conditional carry-in bit, denoted as Cin. The remaining columns detail the specific Boolean logic required for that carry-in across 7 different rounding modes, with the numbers in parentheses referencing the exact logic equations detailed in the paper's text. For the E5M2 format, every evaluated rounding mode is easily achievable. Notice that RZ and faithful rounding both show a 0. This means they require no conditional carry-in at all, making them practically free in hardware. Moving to E4M3, we see the mathematical limits established earlier. The dashes under RU and RD confirm those directed modes cannot be salvaged. However, the critical round to nearest even mode, Rn subscript E, is successfully solved with a straightforward conditional equation. Keep in mind one caveat. These expressions exclusively represent the Boolean logic for the conditional carry-in at the least significant bit, not the entire arithmetic operation. Ultimately, these simple integer additions completely replace complex, traditional mantissa multipliers. Translating those Boolean equations into physical hardware reveals a massive reduction in silicon area. This graph tracks synthesized ASIC area for various E4M3 multipliers, plotting clock frequency in gigahertz against area in square micrometers. Look at the long dashed line representing the standard textbook implementation for RNE. As speeds increase past 3 gigahertz, its area climbs steeply, exceeding 150 square micrometers before failing to route entirely. Compare this to the solid lines representing the proposed integer-based designs. Both the RNE and RZ modes stay remarkably flat, comfortably consuming under 75 square micrometers while scaling smoothly past 6 gigahertz. Bypassing traditional mantissa multiplication fundamentally shrinks the hardware footprint. These proposed exact E4M3 multipliers drastically outperform standard designs in both size and speed, and even hold their own against the cluster of gray lines at the bottom. However, those smaller comparison designs, like the LAM and FPLM1R4, only generate approximate results. The proposed architecture uniquely matches the footprint of an approximate multiplier while guaranteeing mathematically exact rounding. A dramatically smaller chip footprint usually translates to better power efficiency. Switching from physical area to energy consumption, this graph plots clock frequency against the energy required per computation in picojoules. The thick dashed lines representing conventional textbook multipliers show a severe spike as clock speeds push past 2.5 gigahertz, climbing rapidly towards 0.20 picojoules. In stark contrast, the solid black lines for the proposed exact multipliers maintain a highly stable flat profile near 0.13 picojoules, remaining consistent even at peak frequencies. Crucially, this efficiency perfectly mirrors the state-of-the-art LAM approximate design. Note that these total energy measurements include the fixed power overhead from standard input and output registers, which slightly raises the baseline across all designs. Nevertheless, the comparative advantage remains definitive. The proposed architecture achieves the minimal energy costs typical of an approximation while delivering mathematically exact rounding. ASIC results are promising, but modern AI hardware is frequently prototyped on FPGAs. Moving our integer equations over to lookup tables, this chart presents synthesis results on a high-end UltraScale Plus FPGA. Here, the exact designs are compared against a leading approximate multiplier known as LMUL. Crucially, these benchmarks incorporate the extra hardware logic required to safely handle zero-edge cases. Looking at the E4M3 format in the bottom half of the table, the proposed implementation for RNE requires just 17 LUTs and registers a delay of 1.449 nanoseconds. Compare that to the LMUL reference design on the bottom row. Despite being an approximate method, it consumes 24 LUTs and slows down to a 1.704 nanosecond delay. This pattern holds for the E5M2 format above, where the exact multipliers are again decisively faster and smaller. Notice the dashes under the rounding column for the LMUL rows, coupled with the footnote below, indicating that its architecture does not provide faithful rounding. By relying entirely on those streamlined integer equations, the proposed hardware remains fundamentally faster, smaller, and mathematically exact, comfortably outclassing modern approximate architectures on standard FPGA fabrics. By shifting 8-bit floating point multiplication into the logarithmic domain, this research proves we can achieve mathematically exact results using simple integer addition. Using smart conditional carry-in logic to fix approximation errors, the proposed architecture drastically shrinks silicon area, lowers energy consumption, and reduces FPGA latency compared to traditional designs. While the E4M3 format's mathematical limits prevent directed rounding towards infinity, the overarching achievement remains profound. This approach matches the hardware footprint of approximate multipliers while guaranteeing exact rounding, paving the way for radically leaner AI accelerators.